All right, kids. So one of the more difficult concepts to deal with when you're dealing with circuits is how you handle resistors in series versus parallel, and then you can have them in parallel, but then they add up to like being one big thing. And so what this is going to do is kind of get you through some of the more basic concepts. And then kind of once you see this pattern, then you can kind of figure it out from there. So when you're looking at this, so what I've set up is a battery here with 30 volts, okay? So what that is going to mean is that when I add up the voltage across these have to add up to 30, because when that 30 volts is being dropped out of here, that voltage drop has to be 30 all the way across here. But that doesn't mean that each individual part of that might not be 30, but it's going to add up to equal to 30, and that'll make sense in just a second. So one of the first things that you've got to be able to do is find the equivalent resistance of these circuits, or excuse me, of these resistors. And whether they are bulbs, whether they are resistors, it doesn't make any difference. So here's what you've got. So you've got these two resistors, and these are all 10 ohm resistors. So the first thing you got to do is find the equivalent resistance of these two. So because of the fact they're in parallel, that's going to be 1 over 10 plus 1 over 10, which is going to get you 2, excuse me, and then you're going to take the inverse of all of that. Hold on, let me back up. So you're going to take the inverse of all of that, which is going to get you 5. So the equivalent resistance of these two resistors in parallel has a value of 5. So then this one out here then is in effect like in series. So then I'm going to add that together to 10, and that's going to get me a total of 15 ohms. So here's what's important. These two resistors in parallel have an equivalent resistance of 5 ohms. So when you add resistors in parallel, that actually drops the resistance. Then I'm going to add to that the 10 ohm resistor that's in series with that, and then I'm going to get a grand total of 15. So the total resistance in the circuit is going to be 15 ohms. So 1 and 2 and 3 in effect have a value of 5. I add that to that 10, boom, I get 15. Now, once I get that part of it done, so now I can figure out, okay, well, what's the total current in this? So what I'm going to do to get this current, I'm going to kind of make an arrow go away so I can write in here. So I'm going to come in here and go, okay, now I need to calculate that current. Well, when you look at that, I know that that's going to be 30 volts because that's the voltage of the battery. I'm going to divide that by that equivalent of 15 ohms. So that's going to get me 2 amps. So what that means is that the total current in the circuit is going to be 2 amps. So that means I'm going to have 2 amps here, 2 amps here. Okay, so this is going to be 2 and this is going to be 2. But what's going to happen is that because of Kirchhoff's rule, this is going to get split. So I'm going to have, through part 1, I'm going to have 2 amps, okay, which is going to be here. And then this is going to get split equally between the two, so it's like a river. So both of those are going to be 1 amps, okay? Now, if I want to find the voltage, and you could either like measure that or you can calculate it. So if you look at VER to calculate the voltage, then I know going through resistor number 1, if I take 2 amps, okay, and multiply that by 10, so that's going to get me 20 volts. And then if I take, I'm just using VER, so then here to get this voltage, I'm going to take 1 amp and multiply that by the 10 ohm resistor. So I'm going to have 10 volts and 10 volts. Now, So don't flip out and go, well, Mr. Burkamp, that doesn't add up to 30 because I've got 20, 10, and 10. So your current gets split, but not your voltage. So across this whole thing, I've got a drop of 30 volts. But individually, this would be a 20 volt drop. This thing here would be 10 volts. So in this situation, you've got 2 amps coming in. It splits going here, it splits going here, and then it recombines over here. I got 2 amps, boom, we're off to the races. Okay, so that one's fairly simple only because everything was 10 ohms. Now, the next one it's the same process, but it's a little bit more difficult. So now I've got 3 different resistors of different values. But we're going to start with the same process again. So I need to find the equivalent resistance of these 2 in parallel. So that's 1 over 5 plus 1 over 20. And then I'm going to take the inverse of all of that, and I'm going to get 4. So I've got a 4 ohm resistor here. This is a 10 ohm. So the equivalent resistance is going to be 14 ohms. So here's what you can't do. You can't sit here and go, oh, I'm going to add 10 plus 5 plus 20, and I'm going to get, 35 ohms, and that's my total resistance. You could if all the resistors were in series, but they're not. You have 2 of them in parallel. You have the one in series with that. That's where you've got that. Now, we're going to figure out the current through this. So this is going to be still a 30 volt battery. So I'm going to take 30 volts. I'm going to divide that by 14 ohms. And I'm going to get 2.14 amps. So this is going to be 2.14 amps. Now, here's what's going to be important, is that when I add up these amps, that's got to add up to 2.14. Now, this is where this gets a little bit weird in terms of how you calculate the current that's going through both of these. So this is what I found to be the easiest method. So what I'm going to do is that I'm going to take, and what I'm going to use is this kind of little handy dandy equation that's up here. So what I'm going to do is I'm going to take 1 minus the resistor in each one. So like this is a 5 ohm resistor. So I'm going to take 5. And then I'm going to divide that by the total number of ohms in this portion. So I'm going to take 5 and add that to 20. And we're going to get 25. So what this is going to tell me is that basically this is going to get me like a proportion. So this is going to tell me what proportion of that current is going to go into each one of these. So if you do this math, going through you're going to get 1.71, okay? So what that means is that flowing through the 5 ohm portion of that, that's going to be 1.71 amps, okay? Now, to figure out the portion, the current that's flowing through the 20 ohm, I'm going to do the same thing. I'm going to take 1 minus 20, divided that by 25, and I'm going to get 0.43 amps, okay? So with this one, here's what's important. I'm going to add these two together. If I take 1.71 and add that 0.43, I get the 2.14 amps, okay? So, and then, oh, hold on, I left out one important thing. You have to multiply this by 2.14. I left out that part. You have to multiply that by 2.14, okay? My bad, my apologies, don't flip out. You have to multiply it by the total amps that's in the circuit because otherwise you don't get amps, you just get a number. So you got to take the total current, multiply that by this proportion, which is what's showing up here, okay? And so let me go back up here. So this is this total current multiplied by that, My apologies. Hey, I left out one little step. Back off me. It'll be okay. We all make mistakes. Blame it on the coronavirus. I don't know. But here's how you can check that you got this right. If I take the 1.71 and add that to 0.43, I get 2.14. And that's the total current that's in there. So flowing through the 5 ohm, I've got 1.71. And then flowing through the other one, I've got 0.43. So here's where this is going to be huge. Notice that flowing through the 5 ohm resistor, I've got more current. Flowing through the higher resistor, I have less current. So that's going to be something to keep in mind. And if you think about it, that makes sense because this electricity is going to take the path of least resistance. So with this 5 ohm resistor, there's less resistance. Therefore, it's going to get more of that current to flow through. And again, don't ask the question, well, how does it know? That's not the point of this thing, okay? It knows. Just accept it. Now, to get your voltage. So the voltage here is that I'm going to use a little Ver action going on, right? So I'm going to take my 30 volts and divide that by the current that's flowing through the whole thing, and I'm going to get 2.14. And that's going to get me 21.4 volts. So that 21.4 volts will be the voltage drop across this point. So then on resistors 2 and 3, okay, then I'm going to do the same thing, okay. So with this one, I know I can take my current, okay, which in this case is going to be 1.71. So I'm going to go back up here to get Ver. So these voltage drops here I have to calculate individually. I know this one is just going to have a 30 volt drop. Excuse me, is going to be a 21.4 drop because of the fact that I know how much current is going through here, and I know that's going to have a total voltage drop of 30 volts. This whole thing here has a drop of 30 across this whole thing. So to get the voltage here, I'm going to take the 2.14 volts, excuse me, the 2.14 amps, because that's how much is flowing through this whole thing. And then I'm going to multiply that by the equivalence of the 4 ohms, okay? So I'm going to multiply that by the 4 ohms. I had to keep track of where I had going. And that gets you 8.56. And this one's also going to be 2.14 times 4 ohms, which is going to get me 8.56. So I know this can be daunting in terms of when you use the individual currents, when you use the entire currents, and all this good stuff. But when you're thinking about calculating this voltage, and this is why I'm going to do this lab so you all can go through and you can actually, measure it and test this thing. So here's your steps up here. So when in doubt, make this chart of Ver. You don't have to, but it's very, very, very highly recommended. So if you set up this chart of Ver, here's the most important thing. Find the equivalent resistance. You're going to use this handy dandy little thing right here to figure out the current in each part of that. And then that's going to allow you to be off to the races in terms of calculating that voltage. Okay, so I realize this is all one big mess, but hopefully once you do the lab, this will begin to make more sense. So speaking of the lab, I've already emailed that out. And so here's what you're going to do, is that you're going to go through and you are going to set up a situation like this. And you could either put in 2 9-volt batteries, or you can put in one battery and just change the voltage to 18, whatever works for you. I don't care. That's up to you. But then you've got to put in here, and this is all on the lab, so you're going to have a 40 ohm resistor up there. You're going to have a 10 ohm resistor in series with a 20 ohm resistor. So you can have a 40, a 10, and a 20. So make sure that you choose, I think there might be two different versions of this FET simulation. Make sure you get the one that has a movable non-contact amp meter. So here's how I see this lab playing out. So you're going to be able to hopefully do the calculations, okay? And then once you do those calculations, then come up here and actually test this to see if it makes sense, okay? That's the whole point of this FET simulation, is that it does a really, really nice job of this whole thing. Now, when you get to the second page in section 2, you're going to keep the same thing, but then in here, if you tap that, you can cut that. You're going to put in another resistor of 5 ohms. So pull this in here, boom, reconnect that. Change that down to 5 ohms, okay? So you got a 5 ohm resistor, you've got a 40, you've got the 10 and the 20. So then you're going to go through and you're going to redo these calculations again. When you get to the third page, and I've got a 10, a 40, and a 10, you don't have to build this, but you can. Now, but here's what you're going to have to do. If you're going to actually build the simulation to test this third one, on the batteries, you're assuming on the battery that it has no resistance. In reality, batteries do have some resistance. So if you're actually going to build this circuit to test what's going to happen on on that last problem, then you're going to have to increase that resistance, that internal resistance, to 2 ohms. Okay? So the way the first two problems are set up, you're assuming that you have no internal resistance. In reality, there is on batteries, but the first two problems, you're assuming that you have no internal resistance. Then you're going to go through, and then you're going to, if you're going to actually test the last problem, you have to set the voltage on the battery to 100. That'll make sense when you see the problem. And then turn that internal resistance to 2 ohms. Okay, hopefully that gives you some good ideas on what's going to happen on this deal. Again, if you can't print this out and you just want to answer the questions, that's fine. Make sure on that cam scanner that you're using the batch mode, make sure that you name the files like Keaton Circuit Lab, okay, or Peyton Circuit Lab. And if you don't have that cam scanner app, that tends to work very well. I think some of you are maybe scanning it on a machine and then saving it and then uploading it that way. That doesn't work so well on my end, because some of you, when you get your tests back, you'll see that it's like kind of this wonky small image. So if you can use that cam scanner app and that batch mode and send it directly from your phone to my email, that works best. So if you can make that happen, that would be amazing. Anyway, all right, that's all I got. I will send you another video tomorrow about the bulb lab.